time we were talking about the general form of conservation laws and their application in thinking about conservation of energy, momentum, angular momentum, etc. in electromagnetism. So one can formulate a general form of conservation law as a continuity equation, which says that whatever the local density of stuff there is changing because of flow of that stuff to or from the point, and that flow is related to the divergence of the flux density of that stuff. And if in addition that stuff can be locally created or destroyed, then there can be a source term. So in the context of conservation of charge, this was zero, since charge is neither created nor destroyed, in which case the conservation law took the form of just the flow. But in general, if we have whatever that stuff is, can be created or destroyed, is transferred from one form to another, then we would have a source term there. So in particular, we were looking at the problem of thinking about momentum in electromagnetism. And if momentum is changing, well, we have a force on the sources. So the rate of change of momentum on the sources is related to the force on the sources, which is the Lorentz force. And if we want to think about that momentum as conserved, if momentum is increasing, the charges are gaining momentum, then they get that momentum from the field. So that the total momentum of source plus field, or charges plus field, is the total rate of change is zero. So that allows us to interpret then the integrand here as the rate at which momentum is destroyed by the field and put into the sources, or if we put a minus sign there, it's the rate at which momentum is transferred from the source to the fields per unit volume, locally, at some point in space and time. And from this, with a little manipulation, we wrote down the so-called Maxwell stress tensor, which we interpret as the flux density of momentum. Okay? That is, and it's a tensor because there's two kinds of arrows we care about, the direction of the momentum and the direction of the flow. When we had a scalar quantity, then the flow of a scalar is a vector. The flow of a vector is a rank 2 tensor. And so one could, in principle, express, as we did, the Lorentz force law as equivalently as a local pressure. Remember that flux density of momentum is momentum per unit time per unit area, and that's force per unit area, which is pressure. So stress and pressure are related. Those of you who read the colloquium last Friday heard all about stress tensors of flows of the magma and so forth. It's the same, continuum mechanics. So from Maxwell's equations, given this expression for the rate of creation, we can manipulate the expressions by relating the local sources to the curls and divergences of the field, and with some manipulation, actually doing it right with all the minus signs correct, this is the answer, okay? And what this expression is of the form of a general conservation law, where minus the stress tensor is the rate at which momentum is flowing from the sources to the field per unit area. It's a flow to the field. And G here is equal to the Poynting vector over c squared, is thus interpreted as the amount of momentum carried by the electromagnetic field per unit volume. So we're probably familiar from our previous studies with the idea that electric and magnetic fields carry energy. We talk often about the energy density in the field, E squared, B squared, but maybe epsilon naughts and mu naughts if you prefer. But maybe you're less familiar with the idea classically that the electromagnetic fields carry momentum as well. It's at some level a bookkeeping. If we want to think about energy and momentum as being conserved, if we do work, then the energy is stored somewhere, it's stored in the field. If momentum of the charges decreases, where did it go? It went into the field. But of course, now we, give those fields, they have sort of an element of physical reality. They are objects, especially when we think about them as quantized degrees of freedom, then we're used to thinking about the photons as having energy and momentum. But it's a concept that precedes quantum mechanics. It's a classical field construct. Okay, it's of course the relationship between momentum, energy, and for waves, momentum, the wave vector and frequency through Planck's constant was the quantum piece of that puzzle. All right. Finally, we can also say, we can talk about angular momentum, and we'll just write down the answer, which follows directly here. So the torque on charges, well, the charge, if the source is located at some position x, it would be equal to the integral locally x crossed into the force, which is the force per unit volume. Okay? And this is equal to the rate of change of angular momentum of the sources. And if that angular momentum is changing and total angular momentum is conserved in the universe, then it came from the angular momentum in the field. And so x minus x crossed into rho E plus J cross B over C is equal to the rate of creation of angular momentum in the field. Per unit volume. Okay? And so again, we can do the, we just put basically an x cross everything, and we're done. We have the conservation law for angular momentum. Says that d by dt, x cross g, plus the divergence, play around with this a little bit, x crossed into that is equal to the rate of creation of angular momentum in the field. So, this quantity, x crossed into g, equals x crossed into e at x, the function of time, crossed into b over 4 pi c is equal to the angular momentum density in the field. So the electric and magnetic fields carry energy, generally, momentum, and angular momentum. Now, one of the problems we'll have for homework, probably the most annoying problem you'll have all semester, but you know, it's a favorite of many, is to show how the angular momentum in the field classically breaks up into two pieces. One piece we call the orbital angular momentum, and one piece that looks like spin angular momentum. Now, of course, the notion of spin here is a classical concept. It's in some sense the fact that there's two notions of angular momentum, one having to do with the vector nature of the field, the fact that these are not scalar fields, but vector fields. That's one piece of the angular momentum puzzle. In some sense, when we talk about waves, as we will soon, that has to do with the polarization of the field. But there's another part of the angular momentum which has to do with the sort of the distribution in space of the fields. Even scalar fields can carry angular momentum. And it's one of the things that's often forgotten and confused, that when we go to the quantum theory, photons can carry orbital angular momentum too. They have spin angular momentum and orbital angular momentum, just like electrons. I mean, we do that all the time for electrons. Electrons have a spin angular momentum, and they have an orbital angular momentum. We could talk about the total angular momentum, depending on how they're coupled. But it's a classical field property. Now, the spin itself, in this case, is related to the three-dimensional vector nature of the fields, and since there are three components, quantumly, we associate that with spin 1, right? Because if you have spin 1, then you have 2s plus 1 is 3. So the reason the photon is spin 1 is that there are three components. If you ever wondered why that was true. The electron, of course, is not, its field is not a field with this kind of same vector quantity. It's a Dirac spinner, and that's a whole other story. So it doesn't have that classical field interpretation. But for the photon, we got it here. So, little harbinger of things to come, that'll be in your next problem set. All right. Anybody have questions about any of this? All right. Well, we'll be having lots of fun with this in the current problem set. Okay, so what I'd like to do now is shift gears a bit and talk about the wave solutions to Maxwell's equations in free space. So as you know, the big triumph of Maxwell's equations, and the most amazing thing here is, you know, we had shocking the frog's legs, sticking the magnets in the coils, watching the voltmeter do something. We end up with these sets of equations that we now call Maxwell's equations. And they lead to an important conclusion. The conclusion that electric and magnetic fields propagate together, generate one another, and propagate in free space. as waves. So we start with Maxwell's equations. When we have free space, what we mean is in the absence of sources, so we set the charge and current density to 0. So in free space. And these set of coupled PDEs can be decoupled in the standard manner by taking the curl of the curl equation. So if we take the curl of the curl, that's equal to, in this case, the curl of minus 1 over c dt. The curl of E is the gradient of the divergence of E minus the Gaussian of E. Everyone knows that identity by heart. And we can switch the order of derivatives, assuming all our fields are sufficiently smooth, which we always do. Plugging in the context of free space. Of course, this is 0, and del cross B is equal to 1 over c dt. So this is minus 1 over c squared d squared dt squared of E, or del squared d minus 1 over c squared. Okay, and that the similar thing follows if you take the curl of B, you get the same equation for B. Okay, so these, of course, are the wave equation in 3D. Sometimes we write these equations sometimes you'll see the operator del squared minus 1 over c squared e by dt squared as box. The del m del g. So sometimes you'll see the wave equation written in box e equals 0 and box e equals 0. It's a notation that's kind of fallen out of favor, but you'll see it sometimes. Just like the upside triangle is the del, the box is this operator. Okay? All right, so this is the wave equation. We know that you studied previously, electric and magnetic fields propagate in free space as waves propagating at the speed of light. Now, so I want to spend today just reminding you of some of the very basic properties of the solutions to this. Okay. Now, one thing we have to keep in mind here is that we decoupled these equations. And so, written this way, it seems that there are independently 6 equations. One for EX, one for EY, one for EZ, one for EX, one for EY, and one for EZ. But in fact, that of course is not true. The electric and magnetic fields, so what we see is E and B propagate free space as waves, but E and B are constrained. So they're not an arbitrary kind of wave, but there's very specific properties of these waves that are constrained by Maxwell's equations. Okay? So in particular, we have del dot E equals 0 and del dot B equals 0. That's an important constraint in free space. Moreover, E and B are related to one another. Because if I'm given B, then it must be that E satisfies this equation. And if we have E, then B satisfies this equation. So E and B are related to one another according to Maxwell's equations. And that puts constraints on the nature of the fields. Okay, well, the most important solutions that we look for, so let's look for solutions for so-called harmonic solutions. What I mean by that is fields that oscillate in time with angular frequency omega. Okay? So to do that, the most general form we can write down of a field that has this harmonic time dependence is to express the field as a function of times to make the ansatz is equal to the real part of a complex amplitude, which in general is a function of position, and by important convention we write that as e to the minus I omega t. That is the most general solution that oscillates with frequency omega.
Sorry, question.
Yeah.
What did you say the tilde means? Does that mean it's complex?
Right. So what I'm saying here is this is a complex vector generally. This is a complex vector space. So for example, let's say that E tilde is equal to some direction in space. For now, I'll just start with consider this to be a real vector. At some amplitude and some phase, which depends on position. Okay? So that is one kind of solution we might have. It's a complex vector in the sense that we have this phase. Okay? So if that were true, this would be equal to E hat E0 times the real part of e to the I 5x minus omega t, which is equal to E hat E naught cosine of the phase x, which is minus omega t, which is equal to E hat E0 cos phi cos omega t minus E0 or plus cosine cosine. Yep. a quadrature S. So for this linearly polarized wave, this should be as a function of x. The complex amplitude, or the complex vector here, encodes 2 degrees of freedom. Once I fixed this direction E hat, it encodes either the amplitude and phase in a polar decomposition of the complex vector, or equivalently, the amount of cosine and the amount of sine. Those are 2 different ways, as you know, for a harmonically oscillating function to specify the most general function. Okay? So any harmonic function can be always thought about as some amount of cosine and some amount of sine, or equivalently, some phase shift on cosine with some amplitude. Those are equivalent. Okay? They're like the real and imaginary part of this complex vector, or the amplitude and phase of the complex vector. All right, so when dealing with wave propagation, we quite often start by looking at the harmonic solutions because they form a Fourier basis for an arbitrary signal. So if I think about this as an arbitrary function of time, from Fourier's theorem, we know we can decompose any signal in terms of a superposition of the harmonics. So we concentrate firstly on the harmonics, and then at the end of the day, we take the real part. So often we talk about this in terms of, in electrical engineering jargon, we call this the analytic signal. Okay, and then at the end of the day, we take the real part. Let's just do that. Let's take, so we make the ansatz. So Maxwell's equations in free space for harmonic function in time. So now, I'll keep this in here for the moment. Both E and B oscillating with the frequency, take real part at the end. So, of course, what this says is that with this harmonic dependence, the effect of d by dt is multiplication by minus I omega. That's the nice thing about the Fourier domain, is that derivatives turn into multiplication. So the wave equation then takes the following form. We have d by dt squared is I squared is minus 1, so that becomes plus omega squared over c squared t equals 0, and the same equation for B, for the complex amplitude. Okay? These equations are known as Helmholtz equation. The Helmholtz equation is an equation as a function of 3 dimensions, generally, x, y, and z. Del squared plus a positive number on the field equals 0. Okay? And so again, we can look for solutions to this equation. And again, with this ansatz, we have Maxwell's equations take the form del dot E tilde equals 0, del dot V tilde equals 0, del cross E tilde is equal to I omega over C B tilde. That follows from Faraday's law, turning the d by dt into a minus I omega. And finally, del cross B tilde is equal to minus I omega over C E tilde. So, as before, just to reemphasize, we have separate Helmholtz equations for the complex amplitudes E and B, but they are not independent variables. They are constrained relative to one another, and they're also constrained in 3-dimensional space by the divergence condition. Okay? Now, from now on, I'm going to leave out the tildes, and you just keep in mind that's what I'm talking about. Certainly, improper tildes, because they're too annoying. Maybe you can come to annoying, but you gotta live with me. You don't gotta live with the tildes. At least for a few more months, you gotta live with me. All right. So let's remind ourselves, of course, of the most important solution to this that we typically first consider is to look at the so-called plane wave solutions. So these are not plane waves yet. We haven't said anything about the spatial dependence of E or B. All we've said is about the temporal dependence of E and B. We could have spherical wave solutions to Helmholtz equations, where the wavefronts are spheres. We could have cylindrical wave solutions to the Helmholtz equation. But we're going to start with the plane wave solutions. So the plane wave solutions, well, we know what they are. Let's just make the ansatz now that the complex amplitude for E is of the form some e to the I k dot position. Okay? Where this is generally a complex vector. Maybe I shouldn't have dropped the tilde quite yet. B has the same form. Okay, so if we do that, then, well, firstly, note the gradient acting on this scalar function is what? This is a scalar function, so I can take its gradient. What is the gradient of e to the I k dot x? Excellent. Again, the point of writing things in terms of these kinds of complex exponentials is the derivatives turn into multiplication, right? How do we see that if it's not obvious? Well, of course, this is equal to, you know, the partial x, x hat plus partial y, y hat plus partial z, z hat. So what is the partial with respect to x of e to the I k dot x? Well, that's equal to partial x of e to the I k sub x, x plus k sub y, y plus k sub z, z. And the partial with respect to x is I k sub x back to the exponential. So that's the x component of this. I replace d by dx by I kx. Replace d by dy by I ky. Replace d by dz by I kz. And the suspense is killing me, but that gives me the vector. All right? Don't forget that. Waste your time doing this. Okay, so what that says is when we have the plane wave solutions, well, we already replaced d by dt. Every time we saw d by dt, we replace it by minus I omega. Wherever we receive the del operator operating on the thing, we can replace it by I times the k vector. And thus, the plane wave solution this is going to chance it. K dot x minus omega t, which could be some arbitrary phase, because I've written here some arbitrary phase. It doesn't have to be 0 at t equals 0, position equals 0. It could be whatever I like. And similarly for b. And if we plug that in to the Helmholtz equation, we started with the Helmholtz equation. We replace each del by an ik, becomes k dot k. Right? Del squared is del dot del, which gets replaced by ik dot into ik. And so this is a solution for an arbitrary amplitude if and only if the magnitude of k is equal to omega over c. This is, of course, in free space. And this relationship we call a dispersion relation for reasons that there are no relation to reality right now. What the hell is dispersing? But we'll get to where we find ourselves with that. And similarly, the same equation will hold for B as long as this is true. So both E and B are solutions to the wave equation when this is true. Okay. So just a few points to remind you, very, very basic things. Of course, this solution here, plane wave solution, is periodic in space and time. the period in time, in space, we call the wavelength. So when this is equal to 2 pi, I get to 1 period, which tells us that the period in space is 2 pi over k, wavelength. And the period in time is 2 pi over omega, or 1 over nu. What's nu? C over lambda. Okay? So we have the wave is periodic in space and periodic in time. We also see that the surfaces of constant phase at a fixed time. So if I look at this function, it has a phase which is a function of position and time, right? K dot x minus omega t plus some arbitrary constant depending on where the phase is 0 at time 0 and position 0. And I want to know if I fix time, this is a constant, what is the locus of points, the surface at which this is a fixed value? Well, if we can look at that, we can see if I have a plane, if this is k, then for an arbitrary, this is the origin, and this is my position x, all points on that plane perpendicular to k have the same phase, right? Because it's only the component which is along k that contributes. All the components which are perpendicular to k don't contribute. So all points on the plane perpendicular to k have the same phase. So what we learn here, remind ourselves that the wavefronts, which are equal to these surfaces, that's what a wavefront is. A surface of constant phase, the wavefronts are planes. Infinite planes. Now, of course, we know that plane waves thus, since they have infinite extent, carry infinite energy, and thus don't exist, they're not physical entities, but we focus on them because of two reasons. One, because mathematically they're very convenient. They form a Fourier basis for decomposing physical fields, and they have nice properties. In the same way that we talk in quantum mechanics about position and momentum eigenstates, even though they don't exist. Moreover, they are often good approximations to physical fields. Like if I have a laser beam, which has, it's got a big beam area over near the center of the beam, it's a pretty flat wavefront. It looks kind of like a plane wave. All right. Finally, about this one very simple thing we can see here is what is the phase velocity. It's right over here. So if I look at the rate of change with time of the phase as a function of time, well, that's the partial of this function plus, if I'm moving in space, v dot. So this is saying the following. If I were to move with some velocity v how does the phase that I see on this wave change as a function of time? It changes in two ways. One, I'm moving, so as I move, I see different phases. And the train is moving, or the wave train is moving, so that's the partial. And that's equal to, in this case, minus omega plus k dot v. And if I want this, the phase, if I want to keep up with the phase, the question is what velocity do I have to move at such that, looking out my peripheral vision, I see the same phase at every time. So I want this to be 0, and then this is equal to the phase velocity. And as you see from this, that tells me that the phase velocity is equal to omega over c in the direction of k. Sorry, that's not correct. What am I saying? Omega over k, which is equal to c in the direction of k. All right. Okay, so we know what we have here in a plane wave is a set of planes that are separated by the wavelength lambda that are propagating in the direction of k with the speed of light. All right, where's the eraser? Thank you. Now, moreover, we quickly see from Maxwell's equations del cross, let's see which one do I want to go with here. Oh, yes, okay, right. Let's first start with, where's del dot e equals 0, tells me that I got ik dot e is 0, and similarly for b. Plane wave, which says that k is perpendicular to E and k is perpendicular to B. Follows directly from this condition. And this is we call the transversality condition. That's to say, in free space, the direction of oscillation of the electric and magnetic fields must be transverse to the direction of propagation. That's not true inside a medium, where I might have space charge, for example, in a plasma, where I can have oscillating charge, and I can have a longitudinal component of the electric field along the direction of propagation. In free space, though, rho is 0, and well, it's always transverse to B, because this is always true in free space. Similarly, we have the following kind of relation. So, one thing that's important here is that regardless, if I have a harmonic wave, the complex amplitude of B is related to the complex amplitude of E according to Faraday's law. So given one, I can solve for the other. And in the context of a plane wave, I get that relation. So that should be omega. Right? So, and similarly, we have E is equal to K cross B. K hat cross B. Something went wrong. What did I do wrong?
Would that be a positive? E equals negative I, C over
Yes, thank you. When I have to now, there's a plus sign. Thanks. That's what I did wrong. When you bring down this IK, I times minus I is plus 1. Okay, so that's right. That was minus, that was plus. So, what do we learn from these expressions? K hat here is the direction of K, it's a unit vector. So, what we see here is the magnitude of B is equal to the magnitude of K hat times the magnitude of B, which is equal to the magnitude of E. So in these units, God's units, in a plane wave, E and B have the same magnitude. In CGS units, for a plane wave, the magnitude of E equals the magnitude of E. Moreover,
So in other units, another case?
that's right. In SI units, you may remember that there's a factor of C, right? The magnitude of B is reduced compared to the magnitude of E by the speed of light. Of course, the Lorentz force law doesn't have the C in it. The force is still much less because in CGS you have a V over C. Take into account there. Moreover, so we have the magnitude of B with the magnitude of B. We have K is perpendicular to E and B, and moreover, we see that the direction of B is perpendicular to both K and E according to this right-hand rule. So we have in a plane wave, we have the triad E, B, K. That is to say, the direction of E cross B is the direction of K, and of course the magnitude of E is equal to the magnitude of B, so that's true. So the Poynting vector for a plane wave is equal to C E squared over 4 pi. So the direction of propagation, remember the Poynting vector, which is equal to C over 4 pi E cross B, This is the flow of energy. And the direction of flow in a plane wave is in the direction of propagation. All right, very trivial stuff, just to remind you of. These relations should just be right there at the tip of your brain. Okay, they're not. All right, now what I've written down here isn't quite yet the most general plane wave solution. What I talked about here is a linearly polarized wave. Because I chose that vector E hat in the back, I said consider it to be a real vector. And so what we had here was at some fixed point in time, this is the electric field, the magnetic field oscillates perpendicular, and this is the K vector. And then I sit here, and it comes by me at the speed of light, and it oscillates up and down at frequency omega. Right? Now, what I want to just remind you of is the most general solution will have generally involve more complicated polarization states. So the most general plane wave solution, and of course all I have to write down is the electric field, because the magnetic field follows instantly from this expression. Once I know E, I got B. And I'll write it as a real electric field here. I'll write it in the following manner. Hold on a second, let me remind myself. Right. Okay. All right, so the point is the following. The wave, we said, must be have the electric field vector perpendicular to the K vector. However, in the plane, there are two directions perpendicular to K, which I am calling A and B. So here we are, here's the plane, here's the K vector perpendicular to the plane, and I can choose any two vectors that span the plane, and they're possible plane wave solutions. These are not the E and B fields, these are just two directions in space that are perpendicular to K that form, I'll take as E and B, as A and B, as orthogonal unit vectors that span the plane. So These are vectors which are perpendicular to k and perpendicular to one another. For example, if k hat were the z direction, these could be the x and y vectors. Everyone agree? This is the most general electric field I could have. Okay? So if I rewrite this, I can rewrite this in the complex form in the following way. It's the real part of E hat E sub A e to the I phi sub A plus E sub B, electric field sub B, erase all this junk. E to the I phi sub B, e to the I k dot x minus negative. Okay? That is the most general form of a plane wave. And notice that it's specified by this complex vector. Okay? So this is a complex vector. Amplitude. So now I can specify the wave by something about this complex vector. That specifies the nature of this plane wave. And this lives in a complex vector space. It's a vector space with complex coefficients. Okay? So, the way we typically do that is the following. I'm going to define E naught to be the square root of EA squared plus EB squared. In which case, this complex vector is equal to the following. E0 alpha E sub A plus beta E sub B, where alpha is equal to E sub A e to the I phi sub A over E0, and beta is equal to E sub B over E0 e to the phi B. Alpha and beta are complex numbers. E0 is a real number. Notice that alpha and beta are complex numbers whose amplitude is less than or equal to 1. And also notice alpha squared plus beta squared is equal to 1. Right? Because alpha squared is EA squared over E0 squared plus beta squared EB squared over E0 squared. That's EA squared plus EB squared over E0 squared is 1. So we define epsilon, alpha E sub A, is defined as the polarization vector. Notice that generally it's a complex vector. So I have written here my electric field as E0 times the complex polarization vector k dot x minus omega t. It's normalized as a complex vector, which we're familiar with complex vectors from quantum mechanics, psi star psi, well now it's E star E. Okay? Notice from this expression, if as I move along the wave, say at a fixed position as a function of time, then I will multiply this whole thing by some e to the minus I omega t. So as a function of time, this becomes this vector. Right? Multiplying that whole thing by e to the minus I omega t. And the polarization vector sweeps out some trajectory in the plane as a function of time. Now, because we don't want to say there's a different type of polarization at different times, because the polarization vector is doing something as a function of time, what we say is that we characterize the polarization not just by alpha and beta, but all that matters is the relative phase of alpha and beta. The overall phase of this vector doesn't change the nature of the polarization, it just shows where I am in the trajectory of the electric field. So a polarization vector type, which I'll explain what these types are, remind you that, depends only on the relative phase of the complex numbers alpha and beta. So I might more generally write this as sort of a new polarization vector, factoring out the relative phase between them. Where I have written down so what I have done is I factored out the phase, sorry, that doesn't look right, this is right, e to the phi I phi a. Let's factor out that phase, not the b phase.
Shouldn't it not be a vector on the E?
Correct, yes, thank you. So what I did is I factored out the phase from the first and only keep track of the relative phase between these components and put that overall phase out front. Okay, so now the polarization vector is specified by the relative amplitudes of these guys and the relative phase. Now actually, if it's normalized, there's really there's another constraint, which is that alpha squared plus beta squared is 1. So really they're not independent. Okay, let us then just say a few words, and then we'll pick this up next time, that let's suppose that the relative phase is a multiple of pi. In which case, this is equal to this. okay? This is a real vector. Because these we took as real unit vectors in the plane. And if I were to ask what happens to this vector, then if I were to now ask what is the electric field at the fixed position, let's take the position to be 0, the origin, as a function of time. Well, that's equal to the real part of epsilon E naught e to the I, and I'm also going to take phi a to be 0 for convenience. This is equal to epsilon cosine omega t times E naught. So if I were to look at the electric field vector as a function of time, when this condition is satisfied, what is the trajectory of the vector? Well, it's a line. When cosine omega t is the peak, it's along epsilon. As cosine shrinks to 0, this goes to 0, then it goes to -1. And so the electric field vector goes back and forth along the line. If I'm sitting here watching the wave come by, the electric field vector will sweep back and forth along the line. Hence, we give this the very creative name, linear polarization. And the angle that this makes with respect to the A and B axes depends on the relative ratio of these. So theta here is plus or minus the arctangent of beta over alpha. More generally, and we'll finish this next time, if I have a different relative phase between these two, my general polarization will be an ellipse. So the general trajectory that's swept out by the electric field vector as a function of time, when I'm fixed in space, will be an ellipse. It's a circle when this is a half integer of pi over 2, that is to say pi over 2, 3 pi over 2, etc. And more general, it's an ellipse, and the major and minor axes and how they're oriented depend on complicated geometry. All right? Very good. So, review your plane waves. We'll pick up the polarization bit next time.